Hello there, Wildcats. Welcome to your geometry class. In this video, we are going to discuss about similarity in right triangles. Our objectives are use similarity of right triangle to solve problems. And the second one is use length of relationship of the side of the right triangles and an altitude drawn to the hypotenuse to solve problems. We are going to be using the word hypotenuse, legs, and right triangles, and also geometric mean. Let's jump into our first example. Let us say, I'll just erase this one. When you draw an altitude to the hypotenuse of a right triangle, you create three right triangles. How are the triangles related? We will be using theorem 7-4, which states that the altitude to the hypotenuse of a right triangle divides the triangle into two triangles that are similar. So these two triangles are similar to the original triangle and to each other. So if I'm going to draw a triangle here, let us say, specifically it's a right triangle. Let's say this is my triangle A, B, and C, and it's a right triangle in angle C is a 90-degree angle. Recall that all right angles are congruent. Okay, so we have to remember that because both all right triangles measures 90 degrees. Now this is the altitude. If I'm going to draw an altitude, of course, when you draw an altitude, your hypotenuse here will your hypotenuse and your altitude will be forming a perpendicular lines. Therefore, there is also 90 degree here. So if I'm going to separate, okay, of course, this will be also 90 degree. If I'm going to separate these two triangles, so one will be the blue is, let's say this is my first triangle here that I separated from because I draw an altitude there. So this will be your A, C, let's say this is D, ACD, angle, triangle ACD. That's the first one. And the other one would be, again, it's a right triangle. Let's say this will be your DC. This is now your DCB. And this is your right angle here. So we know that this is angle A and this is angle B. Angle A is here and angle B is here. Now, because, okay, I will make a statement here because angle ADC is congruent to angle ACB. ACB. So ADC, okay, so ADC is congruent to ACB from the bigger one. And angle A is, of course, it's congruent to itself, angle A. Therefore, this triangle, the two triangle here, this one and the bigger one, would be triangle ACD. Our triangle ACD is similar to triangle ABC by a similarity. Okay. In this one also, so this statement will be for that one. This one, if I'm going to make a statement, because angle CDB is congruent to angle ACB, they are congruent, and remember that they share a common angle, which is angle B, that is also congruent to itself. Therefore, your triangle CBD, is similar to triangle ABC by, again, it's AA, similarity. So we can now say that your angle or triangle, I'll just use green color here for our conclusion. Triangle ACD is similar to triangle CBD, and it's also similar to triangle ABC. So basically the three triangles are similar after drawing the altitude of the right triangle. Okay, we go now to example number 2. In example number 2, we have to find the missing length within the right triangle. Given that triangle PQR is similar to triangle QSR, what is the measurement of QS? Okay, so we'll apply the theorem that we already know. And if you are going to redraw that, the two triangles, one of which will be like this. So this is your SQ, this is right angle here, SQR. Okay, and the measurement here is 9 and the measurement here is 15. And then the bigger triangle, if I'm going to redraw that so that we will see the corresponding parts of this two triangles. So this will be your QPR. So I did rotate this one so you can see immediately the corresponding parts. So this is 90 degrees, this is 20 unit, and then this is 15. So we'll just use, because the unknown here, I'll just put X for the unknown, maybe your QS, which is the X here. So we need the QS, which corresponds to PQ, okay? So we need our QS. QS corresponds to PQ. And there's also given here, which is the 15, which is RQ or QR. So we have, and then we have SR, and which is 15 and 15. So we'll just choose one here. So maybe we can use SR because there's two given here. Because this one it's unknown, so we cannot use the 15. So we'll be use SR and QR. And then you just plug in QS is X, and then PQ is 20. Okay, that's 20. And then SR is 9, divide this one by 15. And then again, we have to cross multiply this one. Okay, so you have 15x over 15x is equal to 9 times 20. All right, so our QS now is basically QS is equal to 9 over 15 times 20. We multiply that by 20, so our QS is equal to 12. So we can now say that the length of altitude QS is 12. So this QS here, which is the altitude, which is 12. Okay, next example is we are going to relate altitude and geometric mean given triangle ACB. What is the measurement of CD? Notice that CD is the length of the longer leg of triangle CDB, and it is also length of the shorter leg of triangle ADC. Okay, so by theorem 7-4, the one that we introduced a while ago, ADC is similar to triangle CDB. Use the properties of the similar triangle to write a proportion. So we'll be using that to write a proportion. We have AD corresponds to CD. Okay, AD corresponds to CD. Okay, and then that is equivalent to CD. That is also corresponds to BD. So CD corresponds to BD. So we are looking at the bigger triangle here and the smaller triangle. So your AD is 6.4 divided by CD, which is unknown, is equal to another CD, which is also unknown, and then BD is 3.6. Okay, and then again, you have to do cross multiplication here. CD times CD will be CD squared. Okay, is equal to, you multiply 6.4 and then 3.6 will give you 23.04. And of course, we are going to extract the root of both sides so that we can isolate your CD there. So CD, the square root of 23.04 is 4.8. Okay, therefore the length of CD is 4.8 units. Remember, you only have two items that are given in there, which is 6.4 and 3.6. However, by using the theorem 7-4, and remember also that we have the CD is the length of the longer leg of ACBD, and CD also is the shorter leg of ADC. And this is a tip for you guys. You can think about the geometric mean in another way of F geometric mean as x squared is equal to AB. Then x is the geometric mean of A and B. Okay, let's proceed with the next example. Example number 4. Relate side length and geometric mean. So given in this example, triangle RSC, what is the measurement of RT? So we are looking at RT, which is the X. Now, if you have difficulty identifying the similar triangle, remember that you can draw them separately, and was done in just like what we have in our example 1. So again, by theorem 7-4, it's very important that we have to justify our answer using theorem. RST is similar to RTU. Use the properties of the similar triangles to write a proportion. So I'm going to write a proportion here. Again, if you are having difficulty, you can redraw that. Let's say RS is correspond to RT. So this RS here corresponds to RT. Okay, and then is equal to RT corresponds to RU. And then you just plug in those items there. RT is the geometric mean of RS and RU. Okay, we have 15 over RT is equivalent to RT over RU, which is 9.6. Again, you cross multiply, we have RT squared is equal to 144. Therefore, you extract the root of both sides. We have RT is equal to 12. So the length of RT is equal to 12. All right. Next example. Use geometric mean to solve problem. What is the value of x in this example here? So remember that the length of the shared leg of the two similar triangles, the altitude and the larger triangle, is the geometric mean of the length of the two triangles' non-shared legs. So we can now do the relationships that they have. The geometric mean of x and x plus 5 is 6. So I can put there x plus 5 over 6 is equal to 6 over x. Mister, where did you get all of those? So we have x plus 5 over 6, that is the geometric mean, and then 6, okay, over the value of x, okay, because we are looking at the value of x here. They shared a common side, which is the altitude, okay, so we'll be using that. And then you cross multiply, what will happen? So I have x times x plus 5 is equal to 6 times 6 is 36. We have to distribute your x, so we have x squared plus 5x is equal to 36. And then using our, we bring back 36 there, x squared plus 5x minus 36, and using our, that is equivalent to 0, using our knowledge on factoring, so we'll factor this one, which will give us x plus 9 times x minus 4 is equal to 0. So we are going to equate this one into 0. So this one will be x is equal to negative 9. And this one here, x is equal to positive 4. So we only have to get the positive answer. Therefore, the value of x is equal to 12. Remember, length is always positive. Okay. Next question here is an application of geometric mean to find distance. Okay, Zhang is constructing a 4-foot high loading ramp. The length of the back of the base must be 12.8 feet. How long must be the entire base be? Okay, so first is we have to formulate. The ramp and the base form a long leg. The hypotenuse of the right triangle, the height of the ramp, is the altitude of the right triangle. The base of the ramp is composed of the front base, x, and the back base, which is 12.8. So basically, we can just go ahead and make a proportion, which is x, that is corresponds to 4, is equal to 4, our geometric mean, over 12.8. Okay, that's 12.8. And then you cross multiply. That will give us 12.8x is equal to 16, which is, I'm going to divide both sides by 12.8, 12.8. Our value, or x value, is equal to 1.25. Of course, we'll not stop there. So the length of the base, so the length of the base would be, when we add the front and the back, which is 12.8 plus 1.25, which is equal to 14.05 feet. Okay, so the base of the ramp should be 14.05 feet long. Okay, so that's it. If you have any question or clarification, just email me, guys, and then we'll see you in the live Zoom meeting. Bye, guys.